recording. All right. Good morning, Honors Physics. How is everybody? Wonderful. We're all on mute. Today I am going to review with you about lenses in math, and then I'm also going to share with you some interesting ways that we use lenses, like in our eyes and as glasses, so that you understand why we learn about this rather than just learning about it because we said you have to. So let's review. Bye, Grandma Nikki. Love you.
Love you both.
All right. So lenses bend light. Light passes through them, and depending on their shape, the light can either be brought together or spread apart. This converging lens is a convex shape, and that means that it has a focal length that is positive. A positive focal length happens for convex lenses. If it was going to spread the light away and diverge the light, that would make the focal length negative. We want to be really careful about signs. I think you guys are good at the equations, but are just uncertain about what signs to put on things. So this is a positive focal length for a converging convex lens. Light rays that go in parallel will go out through the focus. And so you guys have been practicing those ray diagrams on the worksheet and on the lab. That is a positive focal length because the light really does converge there. Light rays that go in through a focal point will go through the lens again and come out parallel. Don't show light rays bouncing off of the lens. They pass through the lens and they shine through onto the other side of the lens. That's how it's different than a mirror. So these are caved in on both sides, are concave lenses. And anytime you have to trace dotted light rays back, that's what makes it negative. So this has a negative focal length because you had to trace the light rays back behind the lens. Some of you were having trouble on that lens lab because you weren't getting the right answer for the focal length because the image distances for virtual images are negative. The focal lengths for these concave lenses are also negative. So as you have a diverging lens, you have a negative focal length. If any of you have a question or something you want to stop me with, please feel free to unmute yourself and ask me at any time.
Mrs. Fine Ice?
Yeah.
I just wanted to jump on really fast with what you just said because the number one thing, almost every lab I graded, they all had positive positive image distances for a diverging lens like this. And I don't know if that was the same way for you too, but I think only in both of my classes, one person put negative. So when they did the math, all of their focal lengths were calculated wrong because of not making that negative. So I just kind of wanted to jump on that a little bit and really point out what you just said. Like, I hope everyone's paying attention to that has to be a negative number or the math is really off.
Yeah, I agree with that. I think it's because the lab itself was just giving you the magnitude of everything. So the lab was just giving you the absolute value of those distances. And so because it didn't put a negative sign in front of the image distance, you guys didn't choose to put that negative sign on that virtual image. Same thing with the focal length. I think it just gave you the absolute value of the focal length, but really it needed to be a negative value for a diverging lens. And so just like last unit, when you had a diverging mirror, it had a negative focal length. And if you didn't make it negative, none of the rest of your math worked and it was frustrating. Same thing's going to happen this unit. So if you get a concave diverging lens, anytime you trace light rays backwards, that's what that negative sign comes from. All right. Let's go ahead and have you guys give me a thumbs up if signs are making sense and a thumbs down if they're not. You can do that in your participants button. There should be a yes, no, go slower, go faster. You can give a thumbs up or a thumbs down about signs. Do you see it? I got nothing. Mr. Carnduff, do you see it?
I see it. Yeah, I can.
Hey, I got a check mark from Mr. Carnduff. That's a yes. I got,
Did you add those?
I think they're just there. Almost got a thumbs up. Thank you. All right, well, we're gonna move on. Everybody else is like, just walked away from their screen. It's fine. So,
I'm actually going to step out. I'm going to say goodbye. I will talk to you later. Thank you.
bye. Okay, so light rays that come into this lens parallel, they don't spread out like randomly. I think a lot of you guys in parallel, out, away, but you didn't trace them back away from the focal length. So as they go in parallel, the light rays that spread out should line up backwards with the focal point that we provide for you on the ray diagram. So just make sure that you're lining up that diverging light ray with this focal length. And so I've shown you guys these slides before about how to draw those 3 ray rules. I honestly think you should always do ray rule number 2, the one that goes right into the middle of the lens and keeps going, because then you only have to get one other light ray rule right, and that would do the top one. In parallel, out, down, through the focus, or in parallel, out, away from the focus. And then the next one straight through. You only need 2 light rays to cross to form an image. So notice how I put positive DI this time. I really wanted to help you guys with the signs today. So in parallel, out through the focus, go straight through, and now you already have an image formed right here. This is an image. You have to draw in your image. Drawing in your image means where those 2 hit. You're going to draw an arrowhead. You're going to draw a tail all the way up to that principal axis. So in through the focus, out parallel, that's like an extra ray. You don't need all 3 of those. But if they all meet at the same place, you should be happy. So this is a positive image distance. The light rays really meet here. This is projected onto a screen as a real image. This is another ray diagram that people had a real tough time with. For this ray diagram, people were going in parallel and out random angles. I don't know what was happening, but that dot we provided for you was the focal length. So in parallel, out through the focus, in straight to the middle of the lens, keep going through. And then those 2 lines are parallel to each other, which is why no image is formed when the object's at the focus. This is a negative image distance because it's a virtual image. This is how you use a magnifying glass. The object has to be in between the lens and the focus. Magnifying glasses don't cause real images. They don't project them on a screen. Magnifying glasses form virtual, right side up, larger images. So if you trace just these 2 refracted rays backwards, that's what makes it a negative image distance. And they should all meet at that same spot. And then that's going to be where your image is formed. Virtual, right side up, larger. And because of these dotted lines traced backwards, that's what gives you that negative image distance. So we get to use the same equations as we did last unit. And if it says it's a convex lens, you get to use a positive focal length. And you'll do just the same thing you did before to solve for your image distance. If your image distance is positive, that means it's a real image. This one says mirror. It meant to be lens. I copied and pasted it from the old one. But from the lens, if you get a negative image distance, again, a negative image distance indicates that it's a virtual image and that you got to trace that sign, those lines back to find it. So you guys know that these lenses can only form virtual right side up and smaller images. And again, I would do in parallel, out, away from the focus, but this line needs to track back to your focus. And then I would just do this one, the one that goes right in through the middle of your lens. And then where those 2 meet, when you trace this one back, that's your virtual right side up, smaller image. This is a negative image distance. This is also a negative focal length for this type of lens. So a virtual image, negative DI. always right side up, smaller, virtual. Ooh, that's a good slide. So this one has a concave lens, and they only tell you the magnitude of the focal lengths. You need to make sure if it's a concave lens that you're putting in that negative sign in front of the focus. And so that negative value is what's going to end up giving you this negative image value. Use the same equations for magnification. You can either use image distance over object distance or image height over object height. The signs are important. A magnification that's positive means it's a right side up image. A magnification that's negative means it's an upside down image. You need to pay attention to your signs on all of your stuff for your summative. We talked last time about cameras and how they project real images onto a screen upside down. We talked a little bit about telescopes and how the image from one becomes the object from the next, and this is just fun information for you to have. For your microscopes, it's a double lens again, and you are not held responsible for double lenses, so I'm just showing you them so that you know that they're real life examples that you talked about in your lab, how they work. But this is super cool. Your eye has a lens that projects an image onto your retina. This back part of your eye is red. That's how you get like red eye in a picture. And so light comes in through your lens, and what your iris does is your iris is really what controls the size of your pupils. If you turn off the lights, your iris shrinks to open up and let more light in. When we turn on the lights, your iris expands in order to have cover up that light and not have it hurt your eye. And that's like what color your eyes are your iris. Your cornea actually bends some of the light. That's the layer on top of your eye. You could actually touch your cornea with your finger. And so that bends some of the light. Your pupil is just a hole in your eye that allows the light through. And your lens is what projects the image that you see onto your retina. Your lens can actually change shapes and sizes because of these muscles. And so humor me for a second. Would you guys please take your hand, put it in front of your face. I'm not gonna hit you. And look at the fine lines on your hand. Like look at the patterns, shapes on your hands. So you're focusing on something very close up to you. Now move your hand away from your face and look across the room as far as you can see and try to focus in on that far wall. And then go ahead and look back at your hand. Focus in on those fine lines and details. And then go ahead and look back across the room. What you just did was changed the shape and size of your lenses by using your muscles. It was like an eye workout. So your muscles can squeeze your lens or pull your lens in order to change its focal length so that you can focus on things near and far away. These muscles are the ones that deteriorate as you get older and make it harder for you to see both near and far because your muscles aren't going to work for you anymore. So the image gets projected onto the retina, and then all that information gets taken to your brain through your optic nerve. That is also, if the image projects right onto your optic nerve, that's your blind spot. So here's your object. If you have perfect 20/20 vision, your image is formed right onto your retina and you can see very clearly. This is the difference between looking at something close, something far. Close, far, close, far. Those muscles are changing the shape and size of your lens to change the focal length so that you can still project that image onto your retina either way. People that are farsighted, and this is a lot of people, when you are farsighted, you can see far, but you can't see things close up. People that are farsighted, when they project an image, it's too far behind their retina. And so what they need is help bringing that light together better. I say it's because your lens isn't strong enough to really converge that light for you. But really, if you ask an eye doctor, they'll tell you that most eyes are shaped like a tennis ball. And that if you're farsighted, your tennis ball is squished upwards a little bit. So instead of being round, it's pushed upwards, so that you have like kind of a football shaped eye. And so because of the shape of your eye, your lens is not converging onto your retina. So what we need to do is bring something that will converge the light for you in front of your eye. People who are farsighted, they can see far but not near. They need to have this convex lens in front of their eye so that it brings the light in and focus it onto their retina. People that are nearsighted have kind of the opposite problem. Their light is formed together into an image too near before their retina. And so when you're nearsighted, what they say is that instead of having your eyeball shaped like a tennis ball or a basketball, that yours is squeezed, still like football, but on a sideways football, that you kind of have a short but wide eyeball. And so because your eyeball is so short and wide, the light can't spread out far enough to get to the back of your retina. So you need help pushing the light out, spreading the light out. So we put a lens that spreads light out in front of your eye so that that image can be formed onto your retina. You can tell nearsighted people because when you look at their eyes through their glasses, their eyes look small because these concave lenses make you have smaller right side up virtual images. So if somebody has their glasses on and their eyes and their face seem shrunken behind the lens, you can just say, I know you're nearsighted. Opposite is true for farsighted. If they're the type of lenses that make their eyes look really big or their face look really big, then that means that they're farsighted. So that's just kind of fun. How do your glasses work? How do your eyes work? Information. So I would like for each of you to please either give me a comment or a question about what we covered today. So everybody take a minute to think something you learned, something you still have a question about from what we just went over. And then I'm gonna just call on you guys in alphabetical order by first name as you're listed on my screen to say something that you learned or something you'd like to ask about. So, Elise, we will start with you. All right.
Something I learned today was really how the eye works because I never really understood like farsighted and nearsighted, but now I get it because we just went over it.
And you feel good about it?
Yeah.
Awesome. Thanks, Elise. How about you, Emily?
Yeah, I thought it was really cool to learn about like what kind of lenses like different farsighted and nearsighted people need. So like I learned that this is a concave lens, right? For nearsighted people. And that's why like does their eye do they look smaller or larger?
They look smaller. These concave lenses, when you look through them, they only form the one kind of image. It's always virtual, smaller, and right side up, just like our convex mirrors did. So if somebody looks smaller and right side up, the only way was through a concave lens.
Okay, thank you.
You're welcome. Ethan, how about you?
Well, I thought it was just interesting to kind of how you compare the eye to a lens and I'd always just thought it was not like a lens. It was just like, I don't know. I just thought it was more like human heart and it was just weird and we wouldn't be able to figure out how it works. But now that you're comparing it to a lens, it just makes it really interesting.
Awesome. What's super interesting to me is that because we're projecting real images onto our retina, we see the whole world upside down because all real images are flipped upside down onto a viewing screen. And so all of that information that comes into our eye upside down, our brain through the optic nerve processes it and it flips it back right side up so we can interpret the world the right way. But I think that that's a pretty cool power of the brain to be able to flip everything we see as well. The other thing that we're kind of missing out on doing this digitally, but maybe I could just throw a video on here for those of you that are interested, is in class what we'll do on this day is we will dissect a cow eye or a sheep's eye and show you all the different parts and show you how they all kind of go together. So that is not a mandatory assignment. Some people get really grossed out, but people that are interested, I could throw that on Schoology just so you can see it. All right, thanks, Ethan. Izzy, how about you?
I thought it was really cool that we have like those two muscles that like change the shape of our lens, because I didn't know that that's what happens when you like look at something close up or like look at something far away.
Yeah, I like that too. And I like how you can actually feel them working if you do look at something close and far, like your eyes actually get sore. That's like when your parents say, don't sit too close to the TV screen or whatever. Maybe that's old times, but kind of that idea of it's going to hurt your eyes because it's working your muscles too hard if you're trying to sit too close or too far and strain to see it. But yeah, I think that's awesome too. And that it kind of makes sense that all of our muscles kind of age as we get older, and so do our eye muscles. All right, thanks, Izzy. Jackie, what do you think?
I had a question.
Great.
So in general, will we have to determine that the focal length is negative, or will that be given?
That will not be given. That's a great question. So on the last summative, we told you the magnitude of the focal length for each mirror that we gave out. And so putting that word magnitude in front of it gives you that hint that we're not telling you if it's positive or negative. You have to determine it. So if it's a convex lens, you'll make it positive. And if it's a concave lens, you'll make it negative. But you are the one that needs to know which is which for the summative for sure. Good
Okay,
question.
thank you.
You're welcome. All right, Maddie, what do you think?
I just wanted to say thank you for reinforcing that the image distance and focal length are not always positive, because that completely flew over my head the first time we did notes.
Awesome. You are welcome. Yeah, I think I didn't have it like typed into the screen. And so as I was looking at the different labs, I could tell that people were not sure about signs. And that's why I wanted to put that back in here. So hopefully people watch this if they're not on it live and review signs. Cool. Maggie, how about you?
I thought that it was interesting learning how like eyeglasses or contacts work, because I'm nearsighted and I never really knew how like my contacts worked. But I thought it was like interesting learning how converging and diverging lenses work with like our eyesight.
And that's even how they make your contacts, just like you said. So if you have, I mean, obviously this type of shape is hard to ground onto something that fits your eye, but your contacts will just be thicker in the middle and thinner on the top and bottom if you're farsighted. And if you're nearsighted, which is what you said you are, is that right?
Yeah.
So when you're nearsighted, they have to grind your contacts. Like, it makes sense that this part could fit your eye, but they need to make them thicker at the top and bottom and thinner in the middle in order to make that, correction in front of your eye. So you can almost just even feel the thickness and thinness of your lenses as you're touching them in order to feel the shape of the lens. It doesn't have to be perfectly shaped this way. Anything thinner in the middle and thicker on the top and bottom will spread light out, and vice versa is true for the converging lens. And thanks for that teacher appreciation video that you helped organize as well. And thanks to all of you that participated in that. It was very cool. Is there anything else that you guys would like from me? We have for this week, today you have a Mastering Physics assignment. I also made you a Schoology practice quiz about signs, just because I saw that that was a struggle. It's only 5 questions, but just good to practice. And then Thursday will be our summative. And on our summative, it's not just going to be lenses this time. Our summative is going to be refraction and lenses. You know how we had 2 labs? Really look at your feedback from both of those labs to make sure that you can solve a problem from each of them. Feeling good? Thumbs up. Thank you, Emily. All right. Well, then I will let you guys get going, but feel free to email or post to a discussion board if you have any other questions, and have a lovely day.
Thank you.
You're welcome. Bye-bye.
Thank you.
Thank you.
You're welcome, everybody.